Charles Seagrave, and I'm the inventor of a new system called LASSIE. It stands for Large Array of Sound Sensors Indicating Excitation. Its use is for visualizing room modes acoustically within a room, measuring sound pressure level at multiple locations, and visualizing the results. So this is a set of 49 sensors, a case for 49, some of them are deployed outside. Each one of these is a sound level meter, but instead of a meter showing sound level or a string of LEDs showing sound level, it's the brightness of a single white LED that shows the sound pressure level. It turns on at 80 dB sound pressure level and is fully bright at 104. So there's a 24 dB dynamic range from fairly soft, medium speech level to very, very loud. And one of these is somewhat interesting, but an array of 49 of them you can locate within a room. Here you can see an array of sensors that are dim in the middle because the sound pressure level is canceling in the center. Each one of these spots on the screen is the video value of a video image of one of the LEDs. So you see the LED here, you deploy them in a room in a 7x7 array, and each spot on the screen in the video represents the sound pressure level at that point. The software analyzes the video frame on a frame-by-frame basis and derives a sound pressure level according to it. So you can set thresholds. Generally, you're looking for green throughout. If you get a room sweep in green, it's all as well. Above green is red, and so on and so forth. Basically, you can see the response of the room to a sound sweep, generally from 20 hertz to 200 hertz, so low frequency. So you do this over a range of about 20 to 200 hertz, which is the area of interest for room modes. Cancellations occur because of the waveforms interact. Once you've got all the data, you can look at it in a 3D plot, and in this case you can swing and view the system from on top, like an eagle's eye view, or from the side, and if it's very bumpy you may have to move it around to see all the various bumps. Because you've taken the scan over a 20 to 200 hertz range, or you can set the levels, set the begin and end points, you can actually scroll through the data and observe the response at different frequencies. So the frequency is shown here on the lower right-hand corner. In this case, at 143 hertz, we've got a significant notch in the response of the room. You can also export the data as comma delimited ASCII, just numeric information of row number and column number with a sound pressure level as the other axis. And you can export a single frame or send an image at a particular frequency, or you can take all the data and send it out for further analysis. The array is actually deployed in a room on a set of tripods. Ordinarily, you set these up to be at listening height. So if your listeners are ordinarily seated, you can set these up on the floor at the listening height, on the back of a couch if that's where they're listening from, just to get them at listening ear height. I typically, 3x3 is kind of small. It works for a demonstration on a tabletop. Ordinarily, you'd use 4x4, 5x5, or a full 7x7. The number of sensors is based on the frequency of interest. Most room modes occur below 200 hertz. 200 hertz has a 5-foot-long wavelength approximately. And if you get sensors at about 18 inches separation, you can actually see both the high points and the low points of an individual wave. The system is also used for setting up PA systems. Directional loudspeakers will be loud in the center perhaps and a little less on the sides. Here, instead of a guy with a sound level meter saying, "It's a little low over here, Joe," you can actually have the sound level meters showing the light and the amplitude all at the same time. So you set up maybe 49 sensors out there in an array, and you can actually point the loudspeaker and see where its coverage pattern is in real time.